So today I will discuss another topic, but I will immediately see how this links with one, which is this WIVERN mission, which is a candidate mission in the European Space Agency Earth Explorer 11 program. And this mission will measure global in-cloud winds, clouds, and precipitation. So, well, basically, just to keep going with the story, yes, I met Pavlos basically in 2008. At that time, actually, I was in Bonn, and we started actually working on healthcare. And I remember I was working essentially on the simulation of the Doppler. And yes, we started with the NISA project, and then basically in the years afterwards, we did a lot of studies. We looked at pointing issues. So we wrote several papers. At a certain point, because they were only saying the launch will be in 2 years, the launch will be here. So I thought, well, okay, I will start really working at this thing seriously when I will see that the launch is 18 months. Actually, indeed, when you see that the launch date is 18 months, then you are sure that you will launch the mission. Because essentially, at that stage, you start, you basically are sure that the mission will start because it means that all the instruments are ready and they start basically the standard procedures. When you arrive at 18 months, you are sure that you will launch, essentially. But at that time, you say, okay, let's think about something else. And in fact, we were thinking at other things, other ideas for future missions. And in fact, at that stage, I remember we wrote together a paper on polarization diversity. So we were actually thinking at the Doppler as it was envisaged for healthcare. And we were already thinking, well, we didn't do anything because we were not in the initial project, right? It was Anthony and then the Japanese. But we were just thinking, is that the right way to do the Doppler, or it will be noisy, or we'll have problems, right? At that time, I was thinking, well, for convection, for instance, well, there will be a problem because you have seen the image, the image that Pablo showed is an image which is noisy, first of all, right? It's noisy. The second thing, in the color bar that you have seen for the Doppler, the color bar basically goes from -5 to 5 meters per second, -6 to 6 meters per second. So there is, in Doppler radars, there is a problem which is called the Nyquist problem. Okay? So because in Doppler, when you do Doppler with the radar, you measure a phase. A phase by definition is an ambiguity. Okay? But by definition, you convert a phase into a velocity. You know that you have an ambiguity, 2 pi ambiguity in the phases, right? If you measure 2 pi, 4 pi, 6 pi, it's the same thing. It's a phase. Okay? The phase is a 2 pi, has a 2 pi periodicity. So this means that everything falls back into a Nyquist interval. And the Nyquist interval for healthcare is of the order of, depends a little bit on a parameter which is called the pulse repetition frequency. It's of the order of ±5 meters per second. Indeed, it's good because if you want to measure the classical velocity that we have seen, sedimentation velocity of ice, yes, is 1 meter per second, so it's fine. Droplets, 3-4 meters per second is fine. But of course, if you want to really look at deep convection, then you may end up in trouble. Okay? Okay, so there are other issues, but anyhow. So we were thinking, well, can we do something else? So I can, well, people back in the days have already thought a lot of things. And there is another way to do the Doppler, which is called polarization diversity, which has the advantage that essentially, so that the problem of the essentially the problem of the Nyquist, and so there is a general problem in radars which is called the Doppler dilemma. Okay, which is essentially that you have two things that you have to be sure you want to do. You want to measure velocity, so you have this Nyquist issue, but you have also the problem that you want to have range and ambiguities. You have to sort out range and ambiguities. Right? So, which means that you want to be sure that when you send a pulse and you start listening, you don't want to measure second 3 pecos or third 3 pecos. Okay? So for the atmosphere, right, when you're looking at the atmosphere, you know that the atmosphere is maybe 20 kilometers thick in the worst case scenario. In the tropics, you may have clouds up to 20 kilometers. So you want to profile that atmosphere. So you know how much is the ambiguity that you want, okay? And on the other side, you have this Nyquist problem. And the two are, you have basically to do a trade-off between the two. Now, the advantage of this new technique, which is polarization diversity, is basically completely decouple the two problems. Why is that? Because you use polarization diversity to distinguish the signal. So when you send a pulse, okay, if you send a pulse with a single polarization and a receiver in a single polarization, you send a pulse, you listen for a certain time, which is called the PRT, the pulse repetition time, then you send another pulse. Okay, and you listen, but you are not able to distinguish between the two, right? Because they have the same polarization. But if you send a pulse in, let's say, a horizontal polarization, and then you send another pulse in the vertical polarization, then you are able to distinguish that at the receiver level. You just do a receiver where you receive H and V separately. So in that case, you can solve out this problem, okay? Okay, so basically, yes?
If you target the change the polarization?
Yes, I mean, of course, any technique has its drawbacks, okay? Has drawbacks, its complications, and of course, crosstalk is a problem, yes, perfectly fair, but of course, crosstalk typically is small in atmospheric, for atmospheric targets, okay? So actually, the worst target that is producing crosstalk is the surface. Okay, but typically crosstalk of atmospheric targets is of the order of -20 dB. What does it mean, -20 dB? So this means that if I have a signal of 1 watt, 20 dB less means 0.01 watts. 20 dB is a factor of 100. Okay, so this is the typical crosstalk that we have. Okay, this causes a problem. I will sort it out. Okay. Okay, so basically in this long desert that we had from basically 2008 to the launch, we started looking at these things and trying to see, okay, what could be the next mission? Can we do the Doppler pattern, okay, for the next mission? You have always to think forward, okay? And indeed, basically in 2017, I think if I remember well, we submitted the first proposal to this program, which is called the Earth Explorer program. Now, here you have all the satellites that ESA is responsible for. So there are and EUMETSAT, so there are the meteorology satellite, the Copernicus, and the science. So this is the core of this kind of missions here are the most important ones from the science point of view. They are the cutting edge kind of things. They try to explore new observation methods, new instruments. So, and here you see, of course, there is Earthcare somewhere. Back in the days, Eolus, yes, these were, already approved back in the days. Now Earthcare was approved, I don't know, in 2003 maybe. I don't remember. Okay, so anyhow, how does it work? Well, it works like I always make the analogy with the Champions League. So you submit, I mean, every 2 or 3 years, there is a call, and basically open call from ESA. You submit a proposal. Typically, there are 20, 25 submissions. They down select 4. Then 4 missions, they start doing what I call zero studies. So they do some industrial studies, plus they do some technology studies, plus they do some science studies. They do basically this phase 0 for a couple of years. Then there is the semi-final of the Champions League. So this means the 4 missions go to a meeting, they present all the missions, they debate, and 2 are selected. So we are exactly at this stage. So we have been down selected. So now this proposal that we have done, which is called this WIVERN mission, which I will explain what it is about, what it is about. We were down selected, and now we started last year phase A. Phase A goes on for 18 months. At the end of phase A, there is the final. Okay. So actually, instead of the Champions League, actually it's more, I would say it's better to make the analogy with the marathon. So we are indeed at the last 2 kilometers. That, I mean, if you ever run a marathon, you know that they are the most difficult ones. Anyhow, so next year we will know if we are selected. So what is this mission about, this WIVERN mission? WIVERN stands for with velocity radar Nephoscope. So Nephoscope was an instrument old in the Victorian ages. It was used essentially to track clouds to measure winds. Indeed, this is exactly what we are doing. So we want to use the clouds and the precipitation particles as the tracers of the movement of the winds. And what I want to convey today is simply the idea that, yes, this is a revolution. This is a completely new paradigm to healthcare. Because, of course, the bigger question is, you're just seeing another Doppler radar, is just a duplicate of healthcare. No, this is completely new. It's actually a revolution. Okay, why is it revolutionary? Revolutionary because of two things compared to healthcare. The first is that instead of just pointing nadir, we are doing conically scan. So I always say we are doing what GPM, VPR, what the GPM mission, the global NASA JAXA global precipitation mission. What precipitation radar has done for precipitation scanning. You can see these images if you Google the GPM radar. I don't know if you know GPM. Have you ever seen GPM flying over a hurricane? They map basically the three-dimensional precipitation structure of precipitation. Now we want to do this, the same thing for clouds. You've seen the difference. I mean, the key difference between a low-frequency radar like GPM, KU, KA, and a W-band, the key difference is that you can achieve a much better sensitivity at W-band. Okay, so we are seeing minus 35 dBz from healthcare. WIVERN, with a little bit of integration time, will be at around minus 20-something dBz. Okay. Now, if you do you know what is the sensitivity of GPM? How many dBz? In fact, GPM can just detect the clouds, I mean, the rain that Barros was mentioning before. When there is light rain, yes, is where GPM can detect, but it cannot detect tough clouds precipitation, which is lower than that. So actually, the sensitivity is of the order of 12 dBz. The KA actually was supposed to have a little bit better, it's a little bit worse, 15 dBz. Okay? So this means that this guy here can really see the big stuff, the precipitation, the big particle, the big gas particles. But really, we cannot map all the clouds, all the cloud structure. This is what we want to do, and we want to do wide swath conically scanning mode. So we are scanning, so the satellite is in a polar orbiting, so it's moving at 7.6 kilometers per second on the ground track, and it's scanning 400 kilometer radius swath, so 800 kilometers, is doing a full turn every 5 seconds, so 12 revolutions per minute. So it's moving, so it's scanning quite fast. Now, yes?
So for a complete scan, you assume that the thing that it sees is the same.
It sees what it sees. Okay. So it sees, I mean, I will show you in a second what the simulation of what it sees, but essentially it's making a turn, and after a turn, 5 seconds, is advancing. Of course, since it's moving at 7 kilometers per second, is advancing. The satellite is advancing 35 kilometers. So you keep seeing different stuff. Okay. Okay. So this is the first thing, the revolution, the fact that we are doing this wide swath. And I will iterate on this very much, because wide swath means much better sampling. And the sampling is a key word in the talk I'm giving here. Okay, better sampling allows you to do better science. Okay, even if you don't have a sensitivity which is as good as healthcare. Now that number, minus 15 dBz, single pulse. This is the sensitivity of a single pulse. Okay, so if you send only a pulse, but then we know that we can integrate a little bit. Now the same number, if I look at the same number from healthcare, this is minus 21 dBz, single pulse, okay? Healthcare achieves that amazing sensitivity because it's integrating a lot of pulses, sending a lot of pulse, okay? Okay, the other keyword is the polarization diversity. So the fact that we are doing Doppler, the other big innovation is that we are doing Doppler in a much different way. The fact that we are doing Doppler in that different way, as I said, allows us to decouple the unambiguous range problem from the Nyquist problem. In fact, we can achieve a Nyquist which is much, much better than LPR, plus minus 40 meters per second. So this is indeed what allows us to measure horizontal winds. In fact, we are scanning an angle which is 42 degrees. So we are looking, of course, in our line of sight. Remember, when you do a Doppler measurement, you always do a measurement of the line of sight velocity, what you see in your line of sight. Okay? So we will see something which is a combination of vertical velocities and horizontal velocity. Okay? So this is the key measurement that basically this new technology enabled. Okay? And in fact, this is key because on one side we will see the three-dimensional mesoscale structure of cloud systems, which nobody can do on a global sense. And the second thing is that we can see really high winds in cloud system. Think about hurricanes or tropical cyclones. Yes, in terms of what we have at the moment, in terms of the wind observing systems, we have different things. This will be completely complementary. So we have, of course, measurements from geostationary. They just look at, from images from infrared or visible images. If you do just snapshots and you reconstruct the atmospheric motion vectors. You know, I think, Eolus, because you are part of the Eolus validation, so you know exactly what Eolus has done. That case, this measurement of winds in clear sky, a little bit cloudy, but mainly clear sky configuration. Of course, all the aircrafts, when they take off, when they land, and when they measure winds. Radio soundings, yes, but all these measurements are, no real measurements in. First of all, yes, there are no real measurements in condition. Okay, cloudy precipitating system that we don't have really measurements apart from off-ground data. Now, why? And I go back to what Paulus was saying about forecasts, right? So you want to do measurements. Sometimes when you do measurements, you do measurements mainly for two reasons. Either you want to understand processes and you want to understand models, parameterization, and so on and so forth, or you want to assimilate them and make better forecasts. Now, actually, the experience from Eolus demonstrated that Eolus was the most successful mission in terms of impact on the observations. So if you look at, you take an observation of Eolus, that has the highest weight it contributes, let's say, has the best contribution in improving NWP. In fact, actually, ESA is now selling Eolus, that there will be an Eolus 2. Just because of that, okay? So because all the centers, DWD, CMWF, in Meteo France, they assimilate the real Eolus data, and they actually prove that, okay?
By 1 week, they improve them so much that the 2 weeks after, you would have as good as before with Chronos.
So you still have. So, in fact, actually, there was after all this success of Eolus, there was a recommendation from the WMO to say, well, keep doing this, taking wind profiles. Of course, this is strong support to Eolus too, but it's also strong support to this idea that we have in Eolus. So, in fact, it was look at the complement. That is the synergy of all. What we want to aim at is to provide for the first time global observation of vertical structural winds in cloudy region, okay, cloudy precipitating region. So this would be the first era.
Will you be able to measure in precipitation?
And also in precipitation, yes. When of course we are not totally attenuated, when we have good signal, we will see also attenuation. We will see also winds. I will show in a second. So just to confirm this, Meteo France, now we're part of this phase 0 studies, Meteo France. So, question is, of course, when you go to an agency, you want to sell an instrument, they will ask you, okay, what's the impact of these measurements, right? What is the additional gain that I get is from observing the current? Actually, they want actually to tell you what is the gain that you will have when you launch this mission, so in 2034, compared to the actual observing system that you will have at that time, right? So, in fact, Meteo France is this study taking Eolus 2, of course, they have their big data simulation machine where they assimilate everything. On top of that, they put Eolus 2, and on top of that, they put WIVERN, okay, and simulate that.
So they put 2 Eolus. So this is
No, Eolus 2 means that the Eolus 2 is the Eolus that is expected to fly in the 30s.
Then this With twist.
Well, will be two, well, will be one instrument because will be one, the initial idea was 2030, 2035 Eurus to the first one, A, let's say, and then they are two but in different periods. 10 years, they cover 10 years, but 5 years each, okay? So they do this thing and they look at this reduction in the ensemble data simulation spread. Okay, this is a complicated thing, but anyhow, the meaning of this parameter is that if it decreases, okay, if it goes negative, means that you have a reduction in the spread, which is an indication that you will have a very good benefit from the assimilation. So you see, Eurus 2 is the red curve. So a lot of impact went in the upper troposphere and in the stratosphere, millibar. Sorry, hectopascal in the y-axis, right? If you take only WIVERN, is the blue line. Again, pushing towards the left impact. You see, visually, you see that the magnitude is similar to Eurus 2. So this means that we expect WIVERN to have a similar impact to Eurus 2. Okay, which is big because Eurus 2 is already funded, but we are still struggling a little bit, but because it's kind of very, very expensive, becoming more expensive. Now, the key point here is that when you say, but I have already Eurus 2, you could argue, right? Why do I need WIVERN? Because if you put them together, what you get is the green line. So they are completely complementary because you see WIVERN, the blue one, is essentially making the most impact in the mid-troposphere. So they are very complementary measurement because, in fact, Eurus is measuring winds in the sky. On the other hand, WIVERN is measuring winds in cloudy and precipitating conditions. So that, to me, is a very good case for an impact. Now, the other thing you can ask yourself is, well, this Explorer program is not about impact. It is also about impact, but it's about science. So one thing is, for instance, you can say, okay, can we do some science out of these measurements that we do, these snapshots that we get of this mesoscale system and the wind that we measure inside it? Remember, we measure line of sight winds. We don't measure the components of the wind, the vector, the wind vector, right? So the question is, well, can we understand a little bit better this? Well, indeed, what we have done is look at a little bit, for instance, tropical cyclones. Now, what we are doing here, this is a SEM model. This is simulation coming from actually Stony Brook University. So it's a global simulation. And this is a simulation of September 2017. There was Hurricane Irma, basically in the region of the Caribbean. So now the color here means, blue means a lot of integrated cloud content. So of course, when there is dark blue means there are a lot of clouds, okay? So remember, we measure winds in clouds. So we need the targets, we need enough sensitivity, we need enough return. And if we have enough return, if we have cloud precipitation, we will see Doppler and we can measure Doppler. Now you see what we're simulating here. We are simulating that the satellite is flying on an ascending orbit, and it's flying over them. It starts rotating, you start the rotation, and you see how it is rotating, advancing, and cutting through the hurricane system. And this is now, imagine you are cutting through, so you are producing this length per time. So imagine you have Earth here, right? But Earth here now, instead of being a straight thing, it will be a curved thing going around and cutting the hurricane. And this will be, of course, I could put the reflectivity, but here I just put the Doppler. Now you see, plus minus 60 meters per second, the Doppler, because I have this large Nyquist. And this will be signal coming from, as I go through the hurricane, you say, we'll see all these signals. So for instance, you clearly see when you cross the eye of the hurricane, imagine you have, of course, you have a cyclonic circulation around the hurricane. You see this, you see now, you go up at a certain point, as you're passing through, you see you're passing through the hurricane, you pass from very negative to very positive, because you are measuring line of sight winds. Okay? So you see the white line here is the freezing level. And this is essentially what we are plotting here is the winds only where we have targets with enough reflectivity, and I can tell you the number here is minus 18 dBz. So these are all the clouds exceeding minus 18 dBz that will provide us a line of sight wind. You see how many winds we get, and especially in the parts that is above the freezing level, above the line, we'll get a lot of wind. Why do you think that we will not get so many winds in the liquid part? The WIVERN system. Right? So you will have, if there is a lot of rain in the hurricane, there are regions. There are regions where there are quite a rain, but quite a cloudy region we have not much rain. First of all, there is all the glaciated part. Then there are, of course, there is rain, but it's not raining like everywhere. Okay? Yes.
You said that we can raise up to 60 meters per second. But how in clouds, how much you expect? What is the range that you
expect? I mean, think about, right? So actually that one, yes. I mean, the 90 is plus minus 40, but once you have a 90 which is plus minus 40 meters per second, it's okay. In the sense, you will always be able to bias things. 40 meters per second, 40 times 3 is 140 kilometers per hour. Winds in a hurricane?
Yeah, I think.
I can get, I mean, depends on the strength of the hurricane, right? Hurricane. Okay, anyhow. I think I'm taking a lot of time here, but anyhow.
Leave the room.
But
we can continue from the location here, don't worry.
Okay, anyhow, you stop at me. Okay, so actually you say, well, I don't believe your simulations about the hurricane. You probably did something tricky, so on and so forth. So we did a different study here. This is what Frederick did. We have CloudSat. So CloudSat, actually, there is a nice data set built by CSU, the Colorado State University, where they say, okay, let's take the 15 or 17 year record of CloudSat. And the CloudSat flew over several tropical cyclones. Okay, and there are, in fact, if you look at the CloudSat webpage, they don't show warm rain, they don't show ice clouds. They will show all these pictures of the overpass of the hurricane because these are the most, appealing one, right? So what we did was the following. Now, CloudSat is in 94 gigahertz. So this is a real reflectivity measured by an instrument. So these are the values that are real, okay? So the only thing that you have to change with WIVERN is to put in the slant geometry. So the slant geometry, what does it mean? Is that you add a little bit of attenuation. That's it. Okay, so you can reconstruct. Okay, for instance, this is an overpass of whatever Choi 1 Typhoon. Okay, and from the view of CloudSat, you reconstruct the view of WIVERN. And we were very conservative, saying, well, if there is attenuation in the region where it's raining, like we take it out. We don't want to count it. Okay, we want to be sure that we are not really going into the region of massive attenuation. But you see, the kind of values, the kind of wind profiles that we will get, okay? We will get a very nice idea of what's going on in terms of circulation inside the hurricane. But the key is that we have a very large Nyquist, and this is enabled by this technology. So this is statistical. We say, now you have a problem here, right? Because you are, compared to CloudSat, you have less sensitivity. Your instrument is less sensitive. First issue, right? So you will see less clouds. And the second thing is that you will have attenuation. So you will lose something because of attenuation, the extra attenuation that you have because of the slant path. But how much do we lose? So we computed how much we lose using, say, okay, we know how much we see from CloudSat, how much of the cycles we see, okay? How much do we lose? So here the touchstone is CloudSat. Okay, and we are trying to see what is the fraction. So in that case, for instance, the black line, sorry, the gray line is how many profiles per year CloudSat sees in tropical cyclones. And you see the curves are how much you see, of course less, you will see less. If you have attenuation, the slant attenuation, the black, with the same sensitivity of CloudSat, or if you lose attenuation, or if you lose sensitivity, if you go from minus 30 dBz, which is the sensitivity of CloudSat, to sensitivity which are less than that. So you lose something. But still you have plenty of winds there, okay? In particular for the winds, okay, the winds is a rule of thumb always. the winds will produce decent results. This is true for WIVERN, this is true for healthcare, when the signal to noise ratio is larger than 0 dB. So this has, you have to compute with single pulse. Okay, for healthcare, a minus 21 dB. So if you imagine you have your signal from healthcare, you see the reflectivity, you can think, okay, I will see a decent Doppler, not in all the pictures that I see, but only when the reflectivity exceeds minus 21 dB. Same thing for WIVERN. The threshold for WIVERN is minus 18 dB. Okay? So this is the number of things in proportion, you see. Compared to CloudSat, we think we will get a decent Doppler in 50% of the profiles. So if CloudSat sees something in my tropical cycle, I can imagine enough of that, I will measure a very good wind. But now, what is the advantage? Well, the advantage is that, yes, I lose something because I have less sensitivity, but I gain immensely in what? Well, if you think about this, imagine that you have your tropical cyclones, the circle, let's say it's circular, with a radius of whatever, a diameter of 1,000 kilometers. Now you see the cyan line is a possible overpass of Earth here, or CloudSat. And if the satellite is the same, look at what WIVERN will do. Instead of just getting this curtain, which is the cyan one, we get all those ones. So we'll have much better sampling. So I lose, I measure 50% potentially of what the CloudSat sees, but I have the advantage of much better sampling. So order of magnitude, for winds, we think we will see 32 times what CloudSat actually sees. And for clouds, where the sensitivity, you don't need to go to the SNR larger than 0, but you can dig a little bit in to be of the order of 50 times. So this means that we will have an immense number of measurements, for instance, in tropical cyclones. But the same applies for windstorms in the Atlantic, polar lows, and so on and so forth. Now, this, of course, means that we will have a lot of winds, line of sight winds that we can give to the data simulation center. I didn't answer, so here this will answer the fact that, well, hopefully this will improve the numerical weather prediction also for this very important system like tropical cyclones and so forth, right? But there is another question here. The other question is, well, I told you so far, Doppler measurements is always line of sight, right? If the policeman, right, has his radar, it's the same thing, right? The policemen, some of them, they have these devices which are based on Doppler radar, right? If you are going towards the policeman or away from the policeman, that direction will find you if you are exceeding your speed. But if you are passing that way, okay, in that direction, you will not see any Doppler. Measure zero velocity. If you are going 200 kilometers per hour that way, you will not see any because we will measure the line of sight velocity, right? So now the question is, can I do something instead of the line of sight? I don't understand the line of sight. In fact, when I was showing you the plot before, right? When it was passing over the cyclonic center, we were seeing all this change in sign. What is that? I don't understand. You understand wind with vectors, right? So you understand the wind vector. So the question here is, this is the scan of WIVERN. So you have always a forward scan and a backward scan. So this means that if you look at a specific point or a specific region, you may have a loop, for instance, for this region, you will have loops from these directions and loops from these directions. So this means that you will measure the line of sight wind in this direction, the line of sight of wind in this direction. So if these two directions are independent, you can actually retrieve the full horizontal wind. So the horizontal, the U and the V component, the meridional, so the zonal and the meridional component. Of course, you see that this will depend on where you are in the swath. Because for instance, if you are here, so you are exactly corresponding to the ground track. So the satellite is flying in this direction, is scanning in this direction. Now, in that direction, suppose that it's going from south to north, I see, when I'm looking forward, that point, I measure the line of sight in this direction, which is the meridional component. When I am here, and I'm like this, I will measure this component. This is still the meridional. So in this part of the swath, in the central part, I will only be able to measure the meridional part. But in the other part of the swath, I can do the retrieval of the full. Of course, if you have clouds, if I have targets, I need to have targets, I need to have the tracers. Anyhow, so we did a study, try to retrieve the thing. This is kind of the ballpark values that we have for instance, for the hurricane that I simulated before. So for the meridional, more or less the result is independent of the distance from the satellite track of the order of 3 meters per second, which is a good value. We are retrieving the meridional component within 3 meters per second. You see that the U field, so the zonal, it goes to 3 meters per second when you are far away, but it's much bigger when you are close to the ground track. Now, this is about winds so far. I have shown you that we think we will have very good impacts on manual weather prediction. This has been, Meteo France has now consolidated the study doing an OSSI. And we think also that we can use the snapshot that we have to understand better this the dynamics inside tropical cyclones or any meteorological systems of interest. Now, why also this is important for cloud and precipitation products, the sampling? Why this is a revolution compared to CloudSat and compared to EarthCam? Well, again, I show you, this is a paper from Graham-Stevens, 10 years of CloudSat findings, blah, 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 right? It shows this plot here. Actually, this is not from Graham-Stevens. This is a snowfall statistics from Mark Cooley. But CloudSat has been used and has been, it is currently deemed as the best instrument for producing snow climatology. In fact, actually, I can tell you that before CloudSat, we didn't know how much snow was falling in the polar regions. Actually, it was completely missing from the Earth energy budget. Precipitation has to equal evaporation relative to energy. Okay, so there was this part of the precipitation, so the polar precipitation was completely missing from the IP. You know, you typically see this Earth radiation budget annual mean in the IPCC report was missing. Okay, so this was. CloudSat was discovered that there is snow and actually quantify how much snow there is. And indeed, this is the snowfall climatology at 1.1 degree based on 10 years of CloudSat data. Now, what do you see there? What do you see in this? Of course, you see, first of all, yes, you see that there is a lot of snow in the Southern Ocean. There is this part of Greenland which has a lot of snow. But what else do you see? What do you see in this picture? Still, if you look at the details, red, yellow, green, do you think that this is real? Or not? Yes. Yes, exactly. So we are trying to do a climatology at 1.1 degree, even if we have 10 years of overpasses. Yes. That's the difficulty of Alval, okay? You wait forever for this satellite to pass on top of your head, okay? That's the problem, okay? When I say, wow, we put Alval maybe 2 years, you will not do any Alval in 2 years because you will not have statistics to collect, essentially, to sample the phenomenon, okay? Now, and this, in fact, this is the paper from Graham-Stevens. Now, this is, Graham-Stevens is saying, okay, let's have a look at the snowfall rate over not at 1.1 degree, but we want just to see the full continent of Antarctica. Okay? And I look, yes?
Okay, let's make the poll, goes up the poll, and then we continue on. I keep this in mind, keep it. Just a very few of us, we can let you stay here, we'll just go upstairs. And you think that's what I do. Whatever. I have the book that place for this time.
Okay, so anyhow, the bottom line here is, again, in the plots, if I probably start this from the beginning, but I was showing now another slide of of simulating another flight of WIVERN over Antarctica, over the Southern Ocean. Again, you will have this swab, and you will sample 50 times roughly better than CloudSat. So instead of waiting for 50 years, collecting data for 50 years you will never have, you just get the same thing in 1 year. Instead of waiting for 50 months, it's just 1 month.
Overpass, so will it go slower? Supply will go slower than the supply because no.
No. So also the ground track will move extremely fast. Okay, so the ground will move. In fact, if you think about you are illuminating a region, which is a sub-kilometer region also for WIVERN. It will move 500 kilometers per second, very fast. In fact, that's why the reflectivity will not be as accurate as yes. Okay, now there is a sensitivity issue, but there is also a noise due to the fact that you are not integrating many pulses. Right? So I was discussing about this sampling issue, and basically we demonstrate the benefit of sampling looking at snowfall. So what we did practically, we took ERA 5 as a reference. By the way, I didn't show you this. Did I comment on this? I think I didn't comment on this continental snowfall rate from the paper from Graham-Stevens, 10 years of data data. So you see a lot of plots. So what is that? It's the snowfall rate in millimeters per year, the average value over the Antarctica continent, over Antarctica, right? You see all the points, it corresponds to the different average CMIP simulation, climate simulation. So a lot of uncertainty, you see between 150 to 350 millimeters per year. There's not much snowfall going on in Antarctica, but you know, this is the amount. And then there is so actually the yellow number with the bar is essentially the percentile with the mean of this CMIP. Then you have the red dot, which is the ECMWF, average over 10 years of 2000, yeah, the same kind of period. And the blue dot is the CloudSat. So the point here is that even after 10 years of data, can you say with a good confidence what is the right CMIP? Is ECMWF right? Is it the ECMWF wrong? Not clear. There is a lot of uncertainty, even after years and years of data, right? Now, in fact, what we did was the following. We said, let's take ERA 5 as a touchstone, as a reference. We take ERA 5 and we fly over 20 years of ERA 5 data with a single orbit, with an orbit like CloudSat and with an orbit like WIVERN, using the CloudSat sampling and the WIVERN sampling. Essentially, this is what we did. So that is the annual mean snowfall, the top left, from ERA 5. Now, what do you want to do? You want to be able, for instance, on an annual scale, you want to be able to say, okay, I have a forecast, I have a measurements, but what do you want to beat? What is the error that you want to beat? Basically, what we use as a reference is the interannual variability of ERA 5. So when you say, this year, for instance, I want to tell you, well, my measurements tell me that over Antarctica, it's 200 millimeters per year, right? But you want to have an error which is smaller than the interannual variability, because otherwise you use just the climatology, you do better, right? So that's the touchstone. The error is that one. What we did, we basically used essentially a technique where basically we use a S relationship, very simple inversion. We put an uncertainty there. We put it in. We factor in the fact that the radar sensitivity for WIVERN is above minus 20 dBz. But remember, snowfall, if you have minus 20 dBz, you capture all of it in terms of mass. We did this at different scales. Now, for instance, this one is don't remember what is the scale, but essentially the error that we find from WIVERN due to the sampling and also to the uncertainty of ZS at annual scale, and at, if I remember well, this is 2.5 degrees. This is what you see on the bottom panel. and this is the error from Clauser, right? This is normalized NMSC. So 1 means 100%. So you see that Clauser basically is all green, so this means 100% error. At this scale, at this spatial scale and the annual scale, you are not doing for sure better than the mean climatology. But look at WIVERN. WIVERN is doing very well. Okay, and apart from these regions, what are these regions? These regions, very, very high, close to the mid latitude. Of course, is where there is a little bit of snowfall, but look at this climatology, there is very small snowfall, few events. Of course, there the sampling still is a problem because you have few events. First, you have to sample, then even with WIVERN, you'll not be able to sample. But where the bulk of the snowfall is, you see how well we can do, right? And now you can repeat the same experiment. For instance, the classical plot that you always see for when you look at precipitation is the zonal, okay? And the zonal, you average zonally, you average all longitude. For instance, month of January, what we have again data. Again, we got the elements from WIVERN, the blue one, and Ausat, the red one, compared to the climatology. Ausat for zonal mean, annual, sorry, zonal error with the climatology error. So this means, okay, it can start being a little bit useful, but still you need to really smaller than the climatological variability, right? And of course, you can repeat this, as I said, to different scale. For instance, the other important, using the computer, the other important thing, of course, is if you want to do cryosphere, studies about ice sheets balance, right? You may look at the different region of Greenland. You want to say, okay, if I look at this region, the green one, there is a lot of snow in the southern Greenland, okay? If I look at the different time scale, monthly, annual, and so on and so forth, and I compare again my uncertainties due to the sampling and to the ZS relationship from WIVERN and healthcare, what do I get? Again, WIVERN is the thing is the variability is the blue, Clauser is the red, and the gray bar is the climatological variability. Again, you see that typically with WIVERN you can do much better. Right? But this scale, at this spatial and temporal scale, so this tells you at the end of the day, you want to have a product that is able to validate your ECMW. We don't know how much is snowing over Antarctica, okay? ECMWF, you ask people, ECMWF is our best guess. Can we validate these things? Okay, and this is the way to do it. And now we have a tool to essentially assess at which temporal and spatial scale we can do that. And of course, WIVERN, because of the sampling, is able to narrow down the scale and the temporal and the spatial scales. And this is a recent paper by Zhu et al. On validation of CAM6 and M4. So this is validating, trying to validate models, new Earth system models, right? So here, of course, there was some very nice field campaign on the Capricorn 2 campaign. Of course, we know the Southern Ocean is a critical region, that we have critical kind of clouds, combination of superpool layers, mixed phase clouds. And of course, what you see there, they collected a lot of data with WIVERN system going around with the ship. And basically, they built these CFADs, right? So just focus on the top plot, which is everything together. Observation, so this is a CFAD, so reflectivity versus height, statistics. Again, look at that. This is going around with the ship, collecting this WIVERN radar, collecting this CFAD. And look how noisy it is, right? And then they do the same thing with the model, one, model two. Look at the CFAD and you say, well, I mean, do the model look realistic? Yes, they capture this one put too many low clouds, the high clouds are too strong and so on and so forth. Imagine, instead of going around with the WIVERN radar on a ship, trying some smoke tracks, you will have WIVERN going around, sampling, producing these effects much quicker for any region in the world. That's where we will improve substantially, produce things that can really help in pinpointing at issues in the cloud profiles, cloud precipitation profiles of this new generation model, kilometer scale. So remember, our measurements will be kilometer scale. Okay, so our footprint is sub-kilometer. Now, the other big thing is convection and mesoscale convection. Okay, so we need to understand how, well, still don't know globally how these mesoscale convective systems are organized, how much ice they detrain, how much efficient they are in producing precipitation, depending on the environmental conditions and so forth. So in fact, of course, this is one of course of the key question of INCUS, of the NASA INCUS mission that will fly in a few years' time. And of course, I mean, at the end, we want also to understand how all this will change with global warming, right? So you see, it's completely different. You know, some models very less models, they produced typically this popcorn convection. But if you go to larger scales, you typically start having this aggregation. So it's very important to understand these things. And again, think about it. That is a typical mesoscale convective system seen from MODIS. This is essentially an image taken from MODIS, was one of the satellite of the A-train. There was MODIS, and then CloudSat. So CloudSat, now the CloudSat track is the black stuff that you see there. You see the image from MODIS. Of course, MODIS is visible and infrared. So of course, you see the cold stuff, you see the reflective, I mean the highly reflective clouds, but you don't understand anything about what's going on in the vertical. Now, CloudSat comes in, goes through the mesoscale system, and actually you see what this is. This is just the CloudSat curtain going through that system. So you start seeing, oh, well, first of all, I have a big updraft here with actually an overshooting top. Then I have my anvil. Actually, below the anvil, I can see actually there is shallow precipitation. You don't see anything of that from geostationary, right? So this is much better, right? You see the anvil, you see how thick is the anvil. You have an idea with the reflectivity, 20 dB reflectivity, there is a lot of ice water content. You see that. But again, this is just a single track through the mesoscale system. The mesoscale system is hundreds of kilometers wide, and you are just passing through a single thing. Now, you are lucky in this case, you hit a convective core. Most of the time, you may not hit any of those convective core. And now, that's what we will see with WIVERN. Instead of having that single black line, you will have all these blue lines and all these cuts through that. Now, the question is, of course, there are gaps, because remember, that blue line is sub-kilometer, is a kilometer thick line. And between one and the other, there are gaps of 20 kilometers. Now, of course, there is much better sampling, but there are still gaps to be filled. In the case of the mass of the anvil, for instance, you may expect that things are changing radically from kilometer to kilometer scale. If it is convection, I may see, yes, there is, you know, the convection is a phenomenon that works at kilometer scale. For instance, if we want to estimate how much mass there is in this anvil, I will be much better off. We want to understand how much ice is betraying this mesoscale convective system. Instead of just having this, which samples the anvil in these points only, I will have all these samples there. And I guess that with some gap filling methodology, we'll be able to fill the whole thing and compute the full. And of course, combining, remember that this is a snapshot. Remember that the next generation of GEO, they have essentially images every 5 minutes. So the question is that we will have that snapshot. I'm sure 100% that WIVERN will provide a very nice profile of the anvil mass. Now, it will be a question. This is, in fact, the science question is how long can we, with the geostationary images, how long can we actually extrapolate this ice in time, forward and backward, relative to the overpass time? That will be a critical question we need to answer. It can be half an hour, can be an hour, but this will give us the evolution in time of the anvil around the overpass time. And this, I think, is very important from the the reason Paulus was mentioning before, convective systems, of course, how much you strain depends on how much you push up, right? How much convection is strong. Okay, so we will have, generally speaking, the WIVERN mission will have two kind of products. One will be wind products, where we will try, and this will be our flagship products. As I said, main thing will have a lot of impact. We already know that for data simulations. We will try to do also horizontal wind retrievals of the components, UMV, plus still to be understand exactly what we can do in terms of quantitatively estimate updraft velocity. Because again, remember that we are looking for 2 degrees incidence angle, so we are capturing both the horizontal and the vertical component. So if the vertical component, typically we assume that the vertical component, the vertical motion is negligible. We want to only consider the winds, the horizontal winds in stratiform region, where we can assume that the vertical is 0. But when there is vertical component, that can be actually kind of, will come into our signal, so we will try to figure out what we can do. And of course, we have all the cloud and precipitation products, a la CloudSat, a la healthcare, and of course, but with the much better sampling that I mentioned. So to conclude, the key notes here, both thanks to the conically scanning 800 kilometers worth and new Doppler capability that will allow us to measure really high winds. We can really look at horizontal winds. We will also be able to look at the structure of winds, hopefully also the vector structure of horizontal winds. But the other important thing is that because of the sampling, or because of the conically scanning, we will have unprecedented sampling. So we will be able to produce all the data sets that we have produced with CloudSat and we produce with healthcare, like snowfall, like rainfall, condensed mass vertical profile, ice water content profile, and so on and so forth. We'll be able to produce the same thing, but with a much better sampling and therefore much better statistics. And this will be key to validate regional modeling. So we want to go, you know, the important thing of this new generation of models, they want to forecast what happens in a given region. So you need to collect really the cloud and precipitation structure of that specific region. So you really narrow down the spatial dimension. And this can be done with WIVERN. So it will be a revolution. So talking about the revolution, you are very young, but
We're not that young.
you're not that young. So maybe you have listened to this. But back in the days when it doesn't work.
Still playing in the radio Greece.
Singing a cappella.
Whistle it. Why is that working? Okay, anyhow. So this is from the Scorpios. Well, back in the days when there was the wall of Berlin went down, I think you should know, they did this song.
I think you are young for this. Also.
No, I'm not young. I'm not very young. Anyhow, so because we took, of course, for a wind of change was this song from Battaglia.